So before we step away from the set theory for a little bit, I'd like to just do a few example proofs involving sets and statements about sets. And this will not only be a good opportunity to review a lot of the set theory, but it'll also give us a chance to review some of the earlier material on propositions and etc. Let's do close example one. So we'll prove, or let's start by, yeah, A, B, and C are sets. All my examples I'll do, let's use sets A, B, and C, so arbitrary sets. But I want to prove that if, so a conditional statement here, so if A is a subset of B, then A intersect with the set C, whatever it is a subset of B intersect C. And one approach is you can try to draw a Venn diagram and try to figure out why this is true. We need to show this is true for any C, though. So the way we should do this is, let's start by kind of breaking down this conditional. So if A is a subset of B, then we want to prove this statement. And so you'll recall, to prove a conditional, what do? We assume, so let's call this P. This is P right here, and this is Q. If P, then Q. So to prove a conditional, so the idea is we'll assume P is true, assume P, then show Q is true. Okay? And that will prove the conditional. So this is what we're assuming, and this is what we want to show. The thing we want to show is a containment of two sets. So this is a subset of that. And so this is what we're really proving. Like, we should be really focused here. And this is the part that we will use at some point in the proof. We're assuming this is true. But my proof should actually start by, if I want to prove this subset containment, I will let X be, what do? I take an arbitrary element of this set. So I will take an arbitrary element of A intersect C. All right, that's how we prove a set is contained in another. Take an arbitrary element of this. We want to show it's in here, right? So we suppose it's in here. We want to show it's in here. And how do we do that? Well, if it's in there, then what does that mean? We have to kind of unravel what that means. Well, it means that X is in both A and C because it's the intersection. So it's in A and X is in C. All right? Okay. Well, we want to show this as in this intersection. But now we can use this assumption. So since the set A is contained in the set B, we know that X is in B because X being in A implies X is in B. That's what it means to be a subset. Everything in here is in here. So yeah, we know X is in A, so X in A implies also that X is in B. And so let's take stock here. We have that X is in B. We also have that X is in C. That's exactly what we need. We need both of those to show us in this intersection. So we're basically done. But let's just wrap it up by saying since Y is in the intersection, since X is in B and X is in C, so since X is in B and X is in C, our conclusion is that X is in B intersects C. And we're done because we showed an arbitrary element here is there. QED symbol. And let's move on to the next one. Okay. So what are the key points to take away from this one, though? How to prove a conditional statement. You assume P, and then you try to show Q. Okay. What about this? So let's prove that if, we'll do another conditional, if A is a subset of B, then, so I want to prove A and B complement all the things outside of B. I'm actually going to use a term here I haven't used yet, but I'll say what it means. A and B complement are disjoint. So what does that mean? Well, it means what you probably think it means. So this means A and C, these two sets don't share anything. They're completely separate. In terms of our set operation, it means that when you intersect them, you don't get anything. There's nothing that lies in both of them. So A intersect B complement is the empty set. That's what it means. So that this is something tangible that we can try to prove. Okay, so again, we have if P then Q, right? If P then Q. How do we prove that? Well, we can do what we did before with the direct proof. So assume this, try to show that. Here's one potential problem. To show something as the empty set, that seems a bit tricky because we have to show maybe for all elements in here, but there are no elements in there. So that doesn't quite make sense. So how do we show something as the empty set? And there are ways to do it. But my advice would be when you're trying to show something as the empty set, that often calls for either a proof by contrapositive or possibly a proof by contradiction. These are both closely related. Why is that? Well, I'm not sure how to prove something is the empty set. There are no elements in there. It seems a bit abstract. If I try to prove the contrapositive instead, now I want to prove that this is not I want to assume that this is not the empty set, and now I can conjure up an element. Now I know that there's an element, and I have something tangible to work with. So let's try a proof by contrapositive in this one. So, and I'm gonna clue the reader in, and I'm gonna do a proof by contrapositive. So we will prove the contrapositive. And so if you're writing for a mathematical audience, you don't have to write out, the contrapositive is this. They'll be able to figure it out, but let's write it out anyway. So we'll prove the contrapositive, namely, mostly for our own benefit here. Let's make sure we're trying to do the right thing. So namely, if not Q, so if A intersect B complement is not the empty set, then how do we negate this? A contained in B. Well, the negation will be A is not contained in B. So slash through the whole contained sign. So A is not in B. Okay. In other words, there are things in A that are not in B. There's at least one thing in A that's not in B. That's what it means to not be contained. Okay. Great. So that's what we have to do. So how do we proceed? Well, this is what we're assuming. So we assume that. And then we want to take an element in A and show that it's not in B. Right? But first, now that we have something not the empty set, let's actually grab an element there. So Yeah. So we're supposing that is true. This is our new P. So suppose this is not the empty set. I know it's a little bit confusing with the double negatives. So it's not nothing. There's something there. Then there is an element. So there is an X in this thing. In a intersect B complement. And what does it mean? We're just kind of following our nose here. So what does it mean to if X is in this? So then X is in A. X is in A. And for this one X, right, there is an X. And X is in B complement. i.e. X is not in B, right? But that's exactly what we want, because we want to show that A is not contained in B. So we just found an X, it was the one living here, that's in A, but not in B. Yeah, so X is not in B. Therefore, sorry. Or I can say so, that's okay. You want to try to like sort of vary up all the words, connector words, but it's not so important. Where were we here? So yeah, A is not a subset of B. And we're done because we have successfully proved the contrapositive there. So in that case, yeah, we were trying to prove something was the empty set. That seemed to be a little bit tricky to prove that something has no elements. So we decided to prove the contrapositive instead. We assumed that this is not the empty set, and then we were trying to show that not P. So again, the contrapositive is not Q implies not P, and it's equivalent to the original statement. So it's always valid to replace a statement with its contrapositive. You don't change the truth of anything. Let's do one more example. So let's do something with products, actually. Haven't worked with those a lot yet. So let's prove that A union B cross C, so product of two sets, is the same set as A product with C union B product with C. Okay. These are again two sets, both consisting of ordered pairs, so we can take a union of the two. Okay, before we do anything, we should figure out what the framework of our proof is going to be, because this falls into a typical pattern that we've seen. We see two sets, we're trying to prove set equality. So let's just remind ourselves, to prove set equality, what do? We prove each is contained in the other. Prove each is contained in the other. That's the way to do it. So that's where we're going to start. So let's start with this containment. So we'll try to prove this set is contained there. So where do I start? I want to consider an element of this. What do elements of this set even look like? Well, there's a product here. So elements are going to look like ordered pairs. There's going to be something in there and something in there. So let's just kind of review what the product is. So I'm going to consider an arbitrary element here and prove it's in there. That's how you prove the containment, just like we did up here. Okay, so this is arbitrary. X and Y is an element of A union B cross C. Okay. What does that mean? Let's unravel that. Then You probably noticed, by the way, proofs like this, basically 90% of it is just unraveling the definitions. It's like writing down a definition, figuring out what something means. Once you write down what it means, then it sort of hints at where you should go next. So yeah, what does it mean to be in this product? It means that X is in this first factor, A union B, and Y is in the second factor, C. Okay, that's just what it means to be in this product. Let's unravel this. Then, just to make it super clear to our reader, because we were saying something about C, so let's say since X is in A union B, X is in A, what should I put, or and? I should put or, right, because it's a union. So it's X is in A or X is in B. If it were an intersection, I'd put and. I'm trying to prove this in here. So this is actually rather interesting. We have two cases here almost, right? So I think we should actually break this into cases. So case one, well, X might be in A. X is in A. Okay. Okay. Let's think about our goal now, because I'm not quite sure where to go next. So if X is in A, we want to prove it's in here. How would we prove something is in the union? Well, we need to show it's either in here or here. And I think because X is in A, I think we'll have better luck showing it's in here. Sorry, we don't. We want to show X comma Y is in here, the products. But Y is in C, right? And X is in A. So we know, so X is in A. So let's just remind the reader that Y is in C, because it has been a while. So since Y is in C, X comma Y is in A cross C. Therefore, it's also in the union of this with anything, really, but in particular, X is in the union A cross C, union B cross C. Because to be in the union, you only need to be in one of the two. Great. So we did it. Case one. Case two is probably going to look exactly the same. Case two is X is in B. And yeah, this is literally going to be the same. All right. Since maybe we could phrase it slightly differently. This is a stylistic thing. So we have that. Yeah, let's phrase it slightly differently. So again, we have X comma Y is in A cross C, union B cross C. Because it's in B cross C, it has to be in the union. Great. So we're done with this part, at least. We're halfway done with the proof. We completed this part of the proof. And, I think it'll actually be great practice for the viewers to try this half. I'll get us started. So where do we start? We take an arbitrary element of that. So let's, again, let X comma Y. And why is it X comma Y? Because things in here are ordered pairs, something in A and something in C, something in B and something in C. And the union of these two sets, well, things in there are still going to be ordered pairs. So you have an ordered pair. Yes, in here. And then see if you can go from there. So that'll be my starting point. And your goal is to show that it's in here. And then once you finish, you can put a QED symbol at the end. It's very similar to the first part, so nothing too surprising happens. Okay, so having done these examples, we're going to take a bit of a break from set theory, but it will sort of have a constant presence in the remainder of the course. Again, because set theory really is axiomatic foundation of basically all modern mathematics. Okay, thanks for watching.